Good afternoon. Who's here? We are going to wrap up Unit 5 SDS today, and then I'm going to begin Inference unless you have questions. So today till Thursday, I'll take whatever questions you have that you're working on with either BIN or SDS or even probability, and I'll solve those problems. But what I really want to do is start Inference, because if we can spend the next 2 weeks doing Inference, you're going to be in, well, actually 3 weeks, you'll be in great condition for the final exam. So sorry, I'm just trying to find the page that we left off on. So we did a bunch of these problems using the properties. Let me go back to the properties. Let's just recap what theory we're applying. So what we're applying are these two results. Okay. The first, as I mentioned before, so I'll just recap what I said before. Maybe it'll sound a little different and better, more clear. What we're doing is learning about the sampling distribution of a statistic. The statistic that we began with was the sample proportion, the sample count, then the sample proportion, and now looking at the sample mean. Now the sample mean that you get from one sample is a single sample mean that comes from a distribution of all possible means that could have been computed from all possible samples. So the question arises, what is the shape and what are the parameters of the sampling distribution of X bar? Well, it turns out that if you start with a variable that's normal, so it's that regular shape that makes predictions easy, and we know the mean and the standard deviation, then we can expect the same shape in the distribution of sample means, the same mean, and a standard deviation that's smaller by a factor of square root of n. So it's the sample means are much tighter distribution than the original random variable. Then the question comes, what if the original variable, we know we're given the information on its mean and standard deviation, but we don't know its shape. Can we still have the same or make the same assumption that the sample mean should be normal? Well, in fact, in approximation, theory will show that in approximation, yes, the sample mean is approximately the same shape, normal, with the same mean, and again, a standard deviation smaller by a factor of square root of n, 1 over square root of n. So this second property is only the case if the sample size is large enough, and I use n sample size greater than or equal to 25. This is a really important result. This is actually so important they give it a name. They call this the central limit theorem. The central limit theorem. So I'll refer to it in that way, and when you read about the central limit theorem, you should be thinking about this. And I did present you videos in my original playlist that derive those that illustrate how it is that you can expect to see, or how it will look that the sample mean distribution will appear normal. I don't prove the shape of the distribution, but I do prove that you can derive the mean and the variance, and from there the standard deviation of the sampling distribution. So I do prove it here. you do not have to repeat this. This is just really good exercise to practice, again, to practice what you know about the rules of means and variances. So you can step through here and see how I get those results. The sample mean is made up of adding together the observations and dividing by n. So the random variable of the sample mean, is just the random variables all added together and divided by n. So remembering the rules of mean and variances, the mean of a sum of variables is the same as the sum of their means. That's this result that I'm deriving here. So basically the E operator works in this way so that I'm just getting a bunch of means added together, and then the 1 over n factors out. You can just divide by that and see that we expect this distribution of all the possible means to actually be centered at the actual mean. So that makes sense. On average, in other words, I expect that the sample mean, that the true mean will be the mean of all the means. Is that confusing? So we expect on average that the true mean will be your sample mean. And as far as the variance, we use the rules of the properties of means and variances. So for variance, we use the property that, remember, as long as they are independent, and that's what we're assuming, it's an assumption of the sample, that they're drawn independently. Each draw is independent, right? Remember what we're doing when we're sampling. So we don't change the probability of outcomes. We don't change the distribution of the subsequent outcomes each time we draw from the sample. So then the variance of the sum of random variables is just the sum of the variances. So that's how I get that result. And the n comes out. Remembering that any factor from the rules of means and variances, whenever we have a constant or a scalar to deal with, it gets squared. Okay, it gets squared before we take it out. And to simplify, the mathematics shows you that this is just sigma squared over n, for which I can take the square root to get the standard deviation, and that's where that comes from. So again, I'm not going to expect you to prove this, but this is a really neat result, and you should be able to read through that and only have a few questions. And if you do have questions, you should just ask me, and I'll do my best to explain them. So this is the result. It supports the statement of the law of averages. That was this one here. This is the law of averages, and then the second statement is known as the central limit theorem. And I don't prove that, but you take it from me that both statements are foundation to sampling theory, in fact. Okay, so then I asked you to do these problems, and the answers are here. Any questions about these problems, you can let me know today or another day. What I really wanted to focus on is problem number 3. This problem number 3, not that problem number 3, wait. Here. Okay, this, I have a video explaining that, how you do that, so you should practice that. Oh, there's 2, right? I have 2 exercises. 2 different exercises, so you should try and prepare this. Let me know if you have any questions. The answers are here. I think the answers are here for the second one, and the first one is a video. I'm not flipping through these pages too fast, and I hope you have your pages in front of you so it's easy enough to follow. Okay, now what did I want to do? I wanted to do some problems, and how did I miss the problem I wanted to do? I wanted to do problem number 3. Oh no, number 4. Okay, this is the problem I want to do. Okay, so this is the problem here, number 4. Oh, but where is it? Here's a question paper. Okay. Here's a question paper. What I would like you to do, there's only a few of you here, I would like you to attempt this problem. Don't look at the answer, okay? I'm going to leave you to try this. I'm going to leave you for 3 minutes. 3 minutes. Try this for 3 minutes, and I'll come back and see how you did. Okay? Okay, I'm back. How did you do? Did you get anywhere with that? Okay, so what does it say? The age of a woman with a certain disease is 42 years on average, So not of a woman, of women. I'm not even reading this properly. The age of women with a certain disease is 42 years on average with a standard deviation of 2. Okay, so some condition, that's the average age. And it's tight standard deviation, right? So we know when we think about that, it's in 3 standard deviations, that's as high as 48 and as low as 36. So it's not even middle age. These are less than 50-year-old and older than 36 or 35. Okay, so what is the probability that a woman with a disease is over 40 years of age? So let's say I want to report information by decades of age. So I want to go by I want to know for 40 and over. How would I figure that out? So I really can't do much with this unless I make some assumptions. The assumption I'm going to have to make is based on our properties, right? Our law of averages, which is the first statement. This one. And the central limit theorem. This second one is what we're dealing with because I didn't mention at all if the distribution was normal. I didn't say that. So I didn't mention if the distribution was normal, did I? So if I wanted to know what the probability is that a woman with disease is over 40 years of age, then what I have to do, so usually I write it like this. So I'll say X is known to have a mean of 42 and a standard deviation of 2. So I don't know that it's normal. So how could I figure out the probability that a woman with the disease is older than 40? So not to throw you off, but just to make you aware of the information that you need to be able to solve problems. We don't know about the distribution of the ages, the demographic distribution of the ages for these women with the disease. So I can't answer this unless I make some sort of assumption about the distribution. So it doesn't have anything to do yet. I'm not talking about a sample. I'm talking about the variable x. Okay, so I'm not talking about x bar. I'm just talking about x. I'm going to deal with the sample in the next one, see? So I would need to assume something. And you know what? If this was a question on the test, I'll go with whatever your assumption is. You have nothing really to go on for information to prove much, but let's assume this distribution is normal. Let's assume it's normal, then we can solve it. So I'm going to say x is normal with a mean of 42 and a standard deviation of 2. Then I can solve this the regular way. Probability, we could standardize this, 40 minus 42 divided by 2. So it's going to be PZ greater than 1. Everyone sees that? -1, sorry. So I have to go greater than -1. Draw a picture. Remember that at the inflection point is 1 deviation from the mean, and I want to go this way. So I can look at the left side from my tables and subtract off 1, or I can use the left side of the 1 to get the answer. So if you change the direction and the sign, you're going to get the same answer. Okay, you're going to get the same. You can use, if you change the direction and make this a positive, that's the same. So let's just do that. Let's look at 1. What's the probability that the outcomes are less than 1? 0.8413. Okay, so the answer is 84.13%. And let me fix that in case you're in doubt what that is. Okay, so that's that one. So we did that. So that was the question. The question was regarding the original variable. That's different from the next part where let me save this in case something happens. The second part, it's bumping me out. Oops. So the second part says, in a sample of 100 with the disease, so now it's a sample. When it's a sample, I'm going to use the sampling distribution results. What is the approximate probability that a woman, look at the keyword here, approximate probability that a woman with a disease is over 40 years of age? Provide a formula that explains your answer. What assumption are you making, or what theorems are you appealing to? So in the first part, I had to make this assumption to actually answer the question somehow. Yeah, you could have made another one. You could have said you assume it's exponential, if you know what that is. Or you could say you assume it was Poisson, if you know what that is. But that's what I assumed, and that's what I got. If you did that in a quiz, that would have been totally fair for you. In this problem, I'm saying I want the approximate probability, and again, there's no mention of whether it's a normal distribution. So what I'm going to do is I'm going to appeal to what it's asking me, what theorem. I'm going to appeal to the central limit theorem. So I'm going to say central limit theorem, or how about if I type out the result of the statement of the central limit theorem. The statement of the central limit theorem is if x is distributed with a mean of mu and a standard deviation of sigma, as long as, in this case, n was 100, so then x bar, the sample means, are approximately normal with the same mean, but it's a tighter distribution. It's much more less volatile than the original distribution of the variable. So let's answer, so how does that fit in the problem? The question was about 100. What's the approximate probability? So the same question about 40 years of age, but in a sample. So if I took a sample of 100, what would I expect to see? what would be the chance that a woman was over 40 in a sample of 100? Well, where X, let's put the numbers in. So X is going to be have a mean of 42 and a standard deviation of 2, n is equal to 100. So X bar is approximately normal. Even though the original variable wasn't normal, the central limit theorem allows me to assume, I can put CLT for central limit theorem, allows me to assume that this distribution of the sample means is normal with a mean of 42 and a standard deviation of 2 divided by 100, which is 0.02. So I can answer now the probability that X bar is greater than 40, standardizing this, so notice the standard, right? The standard deviation is so much smaller. This makes the number of deviations from the mean much higher when you divide by such a small number. So 40 minus 42 is negative 2. And then divided by 0.02 is negative 100. So it looks funny, but the point is that we went way below the mean, way below the mean. We are 100 standard deviations below the mean. So it's actually certain that we're going to see the ages in the sample more than 400. We expect 100% of the sample to be over age 40. Okay, so I did that mathematically. Now you got to think of it conceptually to really understand what happened there. I'll give you a moment to look at that. So you know, you can copy out your answers in your own time, reviewing the video, or copy it now, or just look at the answers in the solutions here that I provide you with. Okay, the answers are all worked out here for you to see on page 43. Okay, so I think I'm done with SDS. So far then, you know about this set of formulas. This is for, actually let me write it like this. This is for X count, right? This is the count variable. It counts the number of successes in n independent tries. Number 2 is about p hat, the sampling sample proportion. And the third is just what we discussed now. It's a little bit yesterday and a little bit today. This summarizes the results for X bar, the sample mean. So these are all, these are summaries of what we discussed the last few weeks. For SDS, and SDS. All right? So that's what's here. mostly SDS. But these results are critical in inference. Actually, this is also bin, isn't it? Let me put that down. So this is also bin in here. So you have the results from Unit 5 in the first 3 points. So as I said, print out the formula sheet, keep it beside you. You should feel very comfortable with these formula by the time you take the final exam. Okay, you shouldn't be rustling through your papers. If anything, take the formula sheet and maybe, I don't know, shrink it like this and put points, beside it, so you have all the things you need to work with for your final exam. Just use this formula sheet. Try not to have to go through your book or your notes. That wastes time. Okay, so here we are. Inference. Inference is summarized in these 3 rows. Let's see how much I can do today, but I think we can make significant progress. I'm going to start here. I usually start here. These formulas should look familiar. I'm going to repeat what I want you to really look at right now in these 3, in this first row. You see P in various forms. You see P hat, you see P star, and you see P sub 0. But you never see P. Okay, you see P hat, you see P star, and you see P sub 0, but you never, which we actually call P naught, but you never see P. What is P? Let's recap what P is. P is the true proportion. It's the percentage of people who like the Democrats. It's the percentage of people who survived. You're frozen? You don't see where I am? Hold on. Hold on a second. Everything was going so smoothly. What happened? Yeah, I'm just going to reboot the iPad. I have to apologize that my equipment is old. I mean, it's not that old, but old for a computer, so they're going to have glitches. Even my laptop keeps crashing and I have no way to fix it because everything is closed right now. And even if I buy something, I'm not going to get it till June. So that doesn't make too much sense. So I'm just rebooting. I don't know. I hope I don't have to reboot the OBS. Let's see. I think it's working now. Oh wait, we survived. Well, maybe it didn't save what I did, so I can do it again. Okay, so I'm back on, and hopefully you can all see this. Wasted about 10 minutes there, so I can probably go 10 minutes over without a problem, at least on my end. So if you have to leave at 6, then you can just check back and see the rest of the video. All right, so I had recommended using this formula sheet for your exam. So print it out, keep it near you. You can add formulas onto it on the sides, all right? Or even handwrite it out and put any extra notes that you need, but really, virtually everything you need for the exam is here. So all you need to do is know when to use which formula. And let me outline how you can maneuver on this formula sheet. If you notice, the first the first point is regarding x. X is the count variable. So x is the count variable, and this information has to do with SDS, and this has to do with the bin. All right, so that's all about SDS and bin, Unit 5. For the count variable, the sampling distribution of the statistic x, the number of successes in n independent trials. And then here's the binomial form. If it's easy enough to just calculate one, you can get the exact, or just a few of them, you can get the exact calculation of the probability for the binomial. So the second point is all about p hat. P hat is the sample proportion, and this is the information for SDS, the sampling distribution of the statistic p hat. P hat and x depend on n and p. As you see, the formulas just have n's and p's in them. Okay? Next, so what you're going to do to know if you're going to use this one or this one is just basically if it's regarding the number of successes, you could write that down here if you need to, or where x is the number of successes in n trials, right? And if you're talking about the proportion, this is all about the sample proportion. So that's the terminology. Is the question regarding the number of people, or the number of packages that were lost in the mail, or the number of people with an umbrella? Or was the question about the proportion of people in support of a policy, or the proportion of people who survived a treatment, or the proportion? Okay, so you got to look for those keywords. The third point is about x bar. It's about the sample mean. And this is the information on the sampling distribution of the sample mean. What you need for that is to know the mean and standard deviation, the parameters. And if it turns out that you're being asked about the sample mean, something about the sample mean from the mean from a sample, then this would be the mean and the standard deviation of that. And you would also know the shape. In approximation, you would know the shape of the sampling distribution as long as you knew that the original variable was normal or the sample size was big enough. So this is all summary. If you don't know what I'm talking about, practice, 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 and the summary notes are here. So that's all I'm going to say about that. So you need to rehearse those, practice those problems, tons of problems in the notes for you. That brings us to inference. So these last three rows are regarding inference. So the first row here notice, that's what I was saying before I was notified that you couldn't see my screen. The first row has various p's in it: p hat, p star, p naught. P hat, p hat, p hat, p star, p star, p hat, p naught, p naught, p naught. Okay, that's all it has, but no p. What is that all about? Well, in fact, this is about inference. That means inference means guessing, essentially educated guessing, inferring, okay, using information, using evidence to make guesses and to test guesses. That's what it's about, inference. So inference on the population proportion, sorry, the sample proportion, no, actually, sorry. Let's see, I did that wrong. I'm going to be clear. This is inference on the parameter p. That's what we're doing. We're doing inference on, we're guessing about p, the parameter. Whereas above, I was always talking about the sample statistics, right? The statistics. So these are all about statistics. X is a statistic, p hat is a statistic, and x bar is a statistic, but this inference is now about the parameters. Okay, so that's another way you're going to know not to use the formulas above, but you're going to use those below. If I'm interested in testing or guessing or the chance of, well, anyway, just guessing at what the population parameter would be, in this case P, then I would use one of these. Okay, so, and I'll show you examples of that. So we're going to do this. We're doing inference because we don't know what P is. Okay, so this is how we're going to deal with not knowing P, but we want to estimate P. The theory we use to estimate something we have no information on, direct information, we're going to go indirect. We're going to use a sample and indirectly estimate P using the theory we developed up until now. So we developed a theory about the sampling distribution of the statistic, right? So we developed a theory up here. All of this is the theory for the sampling distribution of statistics. In particular, for the proportion, it's the theory number 2. So this is the theory about the sampling distribution of the statistic if P is known. I'm going to base everything on this theory, but take P away and then test to see if it's good enough or how good my estimate is. All right, so you're going to repeat using these measures. This is going to look very familiar when I go below. Look just below and you see this looks familiar to these. Well, this one anyway. All right, so the theory here is being used in inference down here, even though I don't know P. So let's see what that looks like. Let's start there. I'm going to save this. And I'm going to start with inference. Now I hope you can read through these notes in the interim. It'll make more sense now that I'm going to say a few things about it. I want to start here on page 4. I'll give you a moment to go to page 4. Do you have that in front of you or with you? I'm going to give you a minute, okay? Okay, I'm back. All right, so you have this problem. In a study with a new vaccine, what a coincidence, involving 53 lung cancer patients, 29 survived 5 years after surgery. The approximate 98% confidence interval for the true proportion of patients surviving 5 years after surgery with the new vaccine has endpoints. Okay, so if you've never seen anything like this before, do not despair. I will explain what that means. So what we're going to do first is see what we have here. Let me erase my markings, okay? I'll leave some space to write. Okay, so 53 lung cancer patients. This is your sample size. 29 survived. 29 surviving. So you should be thinking, this is a sample. And I'm looking at successes, survival in this case, right? So X is the number, the count of successes. X is 29. And then I'm told, blah, 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 I want to know about the approximate 98% confidence interval. But the first keyword I'm going to follow is this, the true proportion. So this is a problem about proportions. So the problem about proportion will use the first formula on that formula sheet. So what does it say there? If you have that formula sheet beside you as I asked you to have it, you will have, first of all, we need a p hat. I don't have any p hat here. So the formula actually says that a confidence interval begins with the point estimate. This is called the point estimate. So this is just one single value. P hat is calculated by X, the number of successes in n independent trials, divided by how many. So I can calculate that as 29. I'm too close to the top. 29 divided by 53, and I'll put the answer here. So 29 divided by 53, what is that? Well, it's probably 0.547, right? Because those are all the options there. So that's going to be 0.547, which it is. I keep 3 decimal places just because I'm trying to match it with the options here. And they're using 3. Now what? Okay, so that's my estimate. That's my best guess. 54% of people using this vaccine who have lung cancer will survive. 55% will survive, or 54.7%. But usually, it's not going to be exactly 54.7%, right? So if this was to be repeated in a similar sample or in another sample, larger or smaller sample, that's not, I'm interested actually in the samples of size 53. In other samples of size 53, I might not get exactly 54.7%. So there's some variation, right? Well, we know that. We know there's variability. We know that the sampling distribution of the sample proportion is going to be approximately normal, provided what? Now I'm kind of going a couple of classes back and before the weekend, but remember for p hat, it's approximately normal. after you do that little check, remember the check, n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. In problems, usually that's going to be true. In inference problems, it's going to be true. And the sample size should be large. Large means that the population size is greater than 10 times the sample size. Okay? That's what I wrote there. And it's in the notes. So that's large. It's going to be large. Those characteristics are satisfied. This is a 10 here. And so if that's the case, then p hat is approximately normal with a mean of p and a standard deviation of p 1 minus p over n square root. If you don't know what I'm talking about, go back, do all the exercises and see the answers using this property, okay? So this is the result for proportions. So substituting this in, I'm going to go back. This is going to be, P is going to be, well, what is P? What's P? I don't have P. You see, it's not there. There's no true proportion. It's just that we're trying to approximate the true proportion. So there is no P. My best guess at P is this, P hat. So I'm going to use it in the place of P, and even though this is supposed to be P 1 minus P 1 minus P over n square root, I'll put a P here. I don't know. Let me fix that. I have to keep this clean. If I could only edit. Okay, P 1 minus P over n square root. Okay. So the theory says that I should be able to use this distribution with this mean and this standard deviation, but I don't have P. So what we're going to do is instead use P hat as the best estimate and substitute it not only for the mean, but also for this standard deviation. Okay? The catch is that since I don't have P, and I'm using an estimate of P, we have to give this thing a new name. Okay, so this is called the point estimate. It's the estimate of the mean, and we're going to call this not the standard deviation, we're going to call it the standard error. So let's calculate that. P hat times 1 minus P hat over n square root, that's going to be 0.547 times 1 minus 0.547, and I prefer not to put the formula. I just put the number in there that I've actually calculated before because it just gets messy. 4,528 would be 1 minus 0.547. Actually, sorry, let me I'm going to take the rounded value and make this a 3. Divided by 53 with a square root around it. Okay, so that is how I calculate what's called now the standard this is called the standard error, not the standard deviation, even though it is the standard deviation of p hat, the estimated standard deviation of the true proportion. It is, we give it a new name because we use the sample proportion to calculate it, all right? So it has a different name. So when you calculate that, you will have had the mean and standard deviation. Punch it in. You punch in those numbers. I'll use the rounded numbers so we all have the same answer. So 0.547 times 0.453 divided by 53 equals square root is well, I'll make it smaller. It's going to be 0.0684, or just 3 decimal places, 68. And so, looking at my options for answers, it has to be B or D. B or D. So what's the rest of this? What have I done here? This is actually the confidence interval, okay? This is so what have I done here? Let me explain. There's also a formula sheet in Unit 6. And this is the formula here that I'm using. So I'm taking the point estimate and then I'm going to create an interval. Remember, if I have a symmetric distribution, I can use the mean and standard deviation, right, to make estimates, right? I could say, oh, well, since it's normal, in this case approximately normal, 68% of the observations will be between one standard deviation from the mean, and 95% of the observations, or in other words, 95%, there's a 95% chance of an observation appearing between 2 standard deviations, and there's a chance of 99.7% of it being between 3 standard deviations. So this is actually the estimate for the mean. And this over here is the estimate of the standard deviation And what I'm doing is I'm creating an interval with so many standard deviations from the mean. Now, depending on how many what percentage of observations I want to capture, that's going to determine what the z is. So if I want 68%, that's going to be 1 or approximately 1, and I'll show you to be more precise how we get this value. So if you want to do 1 standard deviation from the mean, then you put a 1 there. If you put 2 standard deviations from the mean, then that's 95%. If you use 1, it's 68%. If you put 3 here, then you're capturing an interval of 99.7% in approximation. So let's see. In this case, the question was, I want to be able to make an interval capturing, what did it say? If we go back, it's at the very beginning, it's page 4. Let me save this. So I want, what does it say? 98% confident. So what that means is that I want the endpoints for 98% in between. So what I'm doing is, if we go, just step back here for a second, what we said is we want to use this theory that the sample proportion is approximately, it comes from a distribution that's approximately normal with the mean of the population proportion and a standard deviation calculated like this. This is the sampling distribution. And using the theory derived by the rules of means and variances, I got these results. And so now what I'm going to use is the properties of the normal distribution to identify a range of values that captures 98% of the observations possible. So to be precise as possible, we need to verify what these endpoints are. Is it 2 standard deviations away? It's a little bit more than 2, isn't it? And it's a little bit more than 2, and it's less than 3 because 3 is 99.7. So I want to get more precise about what it is. So I could use my normal distribution table to figure this out, where this is, well, this would be, there's 98% in the middle, that means there's 1% here and 1% out here, or we would write that as 0.0100. You can go onto your z table and look for that. On the z distribution, you'll see, you should pull it up. In the z distribution, this would be -2 the closest one is -2.3. No, wait. Yeah, that's right. It's -2.33. -2.33. And this would be, because it's the symmetry, this would be positive 2.33. So that is going to be the endpoint. That's going to be the Z star. This is also known as the Z star. I'll put the star on it. The Z star. It's also known, they're not known as the critical values. Okay? Known as the critical values. So which one of the alternatives is 2.33? As I explained before, it's either this one, it's either B or it's D. B is clearly the better answer, right? It's 2.326, which rounds to 2.33. It also has the standard error that we computed, so B is the correct answer. We could have put a 4 on there because that matches. So yes, it's B. So where does this result with 3 decimal places come? That's the other table I'm going to introduce, and I will do that tomorrow because I've already gone 10 minutes over. But I will start with an introduction to that table, and then we will continue with inference. So have a good night, and let me know if you have any questions. As I mentioned, on Thursday, you will have a quiz on SDS. So please send me your questions for SDS, that I may solve the problems or do more problems on SDS. Ask me which ones you want me to complete. And I'll work them out tomorrow, okay? So I'll spend as much time as I have to on SDS, and then I'll get back to inference. Have a good night.